Okay, so in this video we're going to look at what do we do with directed graphs or digraphs, so where the edges actually have a direction that you can go in. So this very first one, you can see that you can go from A to B, but you cannot go from B to A unless you find a different route. So I suppose I can get from B to A by going from B to C and C to A, for example, but I can't get from B to A. So how do we do an adjacency matrix for for this graph? So from A to B there is from A to A there's no edges. From A to B there's one edge. From A to C there is none. Yes, there's the one that's connecting A and C, but it's got a direction of an arrow from C to A, so there's nothing going from A to C. And from A to D there is one. Now there's two, but one's directed in one direction, one's directed in the other. Moving on, B to A there is 0. B to C, sorry, B to B there's none. B to C there is 1. B to D there are none. C to A there is 1. C to B there is none because it's pointing in the wrong direction, the arrow. C to C there is none, there are no loops. And C to D there is 1. D to A there is 1. D to B there are none. D to C there is 1, and D to itself is none. So what you have there are all the edges. And just interestingly, you can appreciate that they're all directed there. 1, 2, 3, 4, 5, 6, 7. And if I add up the ones, 1, 2, 3, 4, 5, 6, 7. So a quick double check makes me realize that I've probably got that right. So that's directed graphs represented in an adjacency matrix. Reasonably straightforward. I'm not even going to bother going through the other ones. They'd be too boring to listen and watch. I'll tell you what I will do. For the purpose of the notes, I will fill them in. There you go, and you can download that as PDF if you want to look at the notes I would be writing.